everybody, let's thank Julia again. And I'm really happy to introduce Bethany Ludwig, who is going to present some really cool stuff I've heard. No, Bethany is I know the stuff. Anyway, so Bethany is a PhD candidate at the University of Toronto, and we've been working in collaborations to find strip stars for some time. So this is going to be really fun. Okay, very good, Bethany. Take it away.
Thank you so much, Elva. So like Elva said, good afternoon. My name is Bethany Ludwig. I use she, they pronouns, and I am a final year PhD student at the University of Toronto. My whole research group, which is composed of Ilva and Maria Drout and Anna O'Grady and Alex LaRoche, they're all here today, which is really cool. I feel immensely fortunate to work with them, and I have some really brand new, exciting updates to share from our collaboration. Also, Anna, who took this beautiful photo on one of our observing runs, like pre-COVID, when you could do that. She defended her PhD 4 days ago. So congratulations to her. I couldn't be more proud. And we also have a new member, Alex LaRoche, who's a quick learner and has a poster up on one of our composite strip star systems. During this talk, I'm going to be talking about all of these things and also current work that I'm doing to characterize specific types of strip star systems that are in binaries with compact objects. So during this talk, I refer to massive stars that have had their envelopes removed by their companions as strip stars. So I mean this specific mass range between subdwarfs and Wolf-Rayet stars. Given that the binary fraction is so high for massive stars and interaction is predicted to be very common, it's a bit bizarre to me that only one confirmation of a strip star in this range has ever been put forward in the literature. So in late 2016, Ilva and Maria met at a conference and they conspired to put an end to that. Ilva, who is a theorist, had built her thesis modeling these strip stars and knew that SEDs of strip stars are brighter in the UV. And Maria, who is an observer, realized that there was a relatively new data set of the Magellanic Clouds that might be able to detect these systems by that UV excess. So in 2018, I started grad school. I became a co-conspirator. I built a UV photometric catalog using archival Swift UVOT data with the express purpose of identifying candidate strip star systems through that UV excess. And what we did is we identified hundreds of candidates in the Magellanic Clouds that do fill the gap between subdwarfs and Wolf-Rayet stars. They're all the things that are bluewards of the zero-age main sequence. In this particular color magnitude diagram, the purple line is a model of where strip stars at different masses are predicted to lie, and the diamonds are, for reference, or known Wolf-Rayet stars in those systems. And so now these large colored circles that you see here is a population of our confirmed intermediate mass stripped helium stars. So we went from like maybe 1 to like 20 or so intermediate mass stripped helium stars, which was quite exciting to do. So taking a look at their spectra, there we go. Modeling it has indicated that these stars have really high temperatures of 60 to 100,000 Kelvin, and even by eye you can tell because there's nitrogen 5 in emission, which only shows up if your temperature is above 70,000 Kelvin. We also see from modeling that they are compact, have very small radii, high surface gravities, and low surface hydrogen mass fractions. You can see ionized helium features in their spectra. They don't look like Wolf-Rayet stars, which is the gray line that's plotted above them, and they are too bright to be subdwarfs. Oops. Right. So all of those things are consistent with predictions for strip stars. And in our sample that we found, we identified like 3 classes of different types of things that we were seeing. In class 1, we see only the strip star. There's no signature of a companion in the spectra. In class 2, we see both. We call these the composite systems, where you see a strip star component and you see like a separate like main sequence companion in it. And then class 3 is where the companion is brighter than the strip star. It still makes sense photometrically for there to be a strip star in the system, but the helium lines are much weaker and the hydrogen is stronger. This is an HRD with Wolf-Rayet stars again at one end, subdwarfs in the other, and our population of strip stars between them. If we add our updated evolutionary models for strip stars, you can see that we do explore the entire mass range of 2 to 8 solar masses, with progenitor masses of 8 to 20 solar masses. This indicates that strip stars should explode as hydrogen-poor supernova. This discovery and modeling has been so exciting and fun to work on, but it's a first step in exploring strip stars observationally. We found them, but now we want to do a lot of things with them. So what's next? So when we went to confirm our strip stars using spectra at the Las Campanas Observatory in Chile, we were only able to do like 1 star at a time. So we went and we got time on the Anglo-Australian telescope, which has a multi-fiber spectrograph, and we observed simultaneously like hundreds of strip stars. And so we hope that like now we can, with this data, like be able to say something about the population statistics of strip stars, maybe even the strip star binary fraction. And also we might be able to explore, because both clouds, the LMC and the SMC, have different metallicity environments, to probe like what kind of effect that has on the strip stars that we see. The other thing that we found in modeling was that, like as a rough estimate, the mass loss rates we were finding for these stars was lower than any expectations that we had before. And so we would like to further constrain this. We have an accepted HST proposal to model the UV portion of the spectrum. And we're working to characterize the different types of systems that we see. Alex Laroche has a poster, as I mentioned earlier, where he is constraining orbital parameters and masses of a composite system. And what I am doing now is I am currently working on the 8 strip stars that we have that have no signature of a luminous companion in the optical spectra. I'll talk a little bit about that right now. There are essentially like 3 reasons why you would not see a companion in the spectra. One is that the strip star is truly alone, like maybe it was disrupted. The other star exploded as a supernova. There was a kick, and the strip star is just out by itself. Or there is a main sequence companion, but it is too faint for us to be able to see it in the spectra. We predict that that would have to be in cases where the main sequence star was very small, like 2 solar masses or less. And the other case is that the companion has to be a compact object. We did RV monitoring of all 8 of these sources, and we find that for every single one, there is evidence of binary motion, so we can rule out the case of it being disrupted. In fact, we see a wide range of periods for these systems, from a few hours to a month. And to illustrate what these look like, I'll pick a case study I've been working on quite closely from our discovery paper, which in that paper we called it Star 3. This is the optical spectra for Star 3. We estimate a temperature of 72,000 Kelvin for it. It has a depleted hydrogen surface fraction, a radius of 0.76 solar radii, a high surface gravity of 5.4, luminosity of 10 to the 4. We see ionized helium in the spectra, weak hydrogen features, and nitrogen 5 in emission. We have 38 epochs of optical spectroscopy for this source. So doing simultaneous line fitting to get RV measurements, we use that in a custom MCMC software known as the Yoker to constrain the orbit, and we find that this isolated strip star is in a tight 4.17 hour orbit, which is quite close. And it is circularized. The eccentricity that we find is very, very small. It has high amplitudes, and our minimum mass estimate is 1.18 solar masses. And if we take this minimum mass and we go and get a MIST model for it, and we calculate what is like the Roche lobe radius for this companion mass in the orbit, we find that for any point during its lifetime, a main sequence star would not fit within this orbit. So we can effectively rule out that second option of having a low mass main sequence star that was just not contributing enough flux for us to see it. So effectively, like, the companion has to be a compact object. Now, like, this plot I made a few days ago, so it's pretty new. It's not finalized, the light curve. I haven't like modeled it yet, but I'm really excited to, and I'm excited to show you. We obtained it using UltraCam, and I have it phased here to our orbital period. And by eye, you can already see evidence of ellipsoidal modulation, which is really cool. It should be able to provide us another constraint on the mass, for instance. And the difference between the peaks is also kind of interesting. I think that is probably a feature of like Doppler beaming. And the amplitudes of that beaming sync up really well and follow along with the radial velocity curve as well, which is also quite neat to see. Yeah, and I'm really excited to see what some of the modeling for this light curve produces. Another thing that we've been doing is I made some predictions for the X-ray luminosity since they're so tight, if there is any material being fed by the winds onto the compact object that could produce like standard Bondi-Hoyle wind accretion from which you would see X-ray. So we have submitted a Chandra proposal for this source, which we hope to hear back from in a couple weeks. I think that those decisions are supposed to come out like early August. And we also took a look at some XMM Newton archival data, and the unfortunate thing is where we found like an upper limit was like just shy of our predictions. So having that Chandra data will be really cool. So finally, I'd like to present like this rough picture using my imagination of what I think could have happened to get the system to where it is today and where the system might be going. And so if you start kind of back here, this is laser. This is present day, where we have our compact object and our strip star. They are very close, so I think it's reasonable to assume that they probably formed out of common envelope evolution, especially since whatever mass that the strip star initially had is not on the compact object. And then just using models that Ilva did, like a progenitor for a strip star of roughly 4 solar masses would be between 11 and 14 solar masses. So if you go from a compact object main sequence, that would have something would have had to happen to get it closer together. So we think that maybe that would have been like Roche lobe overflow, which could have, if you assume is maybe conservative, and like you put everything on it, you can kind of end up with something where you have a system that is 8.5 and 5.8, which kind of like works out nicely, especially because otherwise you would have this like strange thing happening of the lower mass star evolving first, which you could happen, but you kind of want to avoid. And the nice thing about this too is it kind of reflects a lot of models of like what you kind of need to end up getting to something that might produce gravitational waves in the future. So if we kind of follow that along to go forward again, with how close the binary is, the strip star will likely expand again. They're very close. It's like 2 solar radii between them. So if it expands even a little bit, a third phase of mass transfer onto the compact object will happen, and it'll become an X-ray binary. And then soon after, the strip star will explode. And as it's now undergone 3 stages of mass transfer, it would likely then be an ultra-stripped type 1b supernova if the system is not disrupted. And as just like a quick calculation to figure out, is it going to be disrupted or not? If we assume that there isn't a lot of mass transferred during this process, we can say something like if the companion mass is less than 1, it would be disrupted, but we already know that it's not. And if more material did go from the strip star to the compact object, it would go even more in the direction of needing a smaller compact object in order for the system to be disrupted. So we believe that is probably a pretty bound system. Yeah, in summary, we have a wealth of observations now on the elusive massive stars stripped in binaries. We have used these observations to create new updated models. We have placed lower limits on the wind mass loss rates, and we identified a close strip star system with a compact object binary, which is likely the result of common envelope evolution and probably will be a gravitational wave emitting source, and probably will even merge. I did a quick calculation this morning. I think it'll probably merge within like 160 megayears. And we also identified a wider system that straddles the critical mass ratio, which is a really cool system that Alex Roche is working on. This is a picture of when we went observing with me and Anna and Maria and Ilva, and I'm really excited to have them all here. So if you have questions on any kinds of parts of these systems, you should definitely ask them. And yeah, thank you so much for your time.
But for now, the floor is for Bethany. Any questions for Bethany? I think that we have Thomas Tauris already with a hand up.
Thank you very much for this very interesting and great talk.
Thank you.
So just a comment to your evolutionary scenario for the future of this system, if you could go back one slide or two. Yes. So, yeah, just forward one. Yeah. So this system is a very interesting progenitor of some systems that we do know of, where we do have an old oxygen near magnesium white dwarf, which was formed first. And then we have a young radio pulsar orbiting this white dwarf, which obviously then formed in a subsequent supernova explosion. So your binary is a very nice system as a precursor of these systems.
Well, that's really interesting. Yeah.
And remember to take the kick into account when you discuss whether or not it becomes disrupted.
I have some ideas of how I can be a little bit more formal with the kicks. Yeah, I definitely want to do like a really cool, like stellar population stuff. Yeah, cool. Thanks.
I think I saw Eva's hand.
Yeah, thank you for this really exciting talk. It's so nice to see that we can see these systems now, and yeah, I really like what it tells us about the evolution. So I was wondering about the prospects of seeing these systems as LISA sources. Have you thought about this?
That's a really fun question. Ilva has a paper on like subdwarf LISA systems, and yeah, it would be like really interesting to like. Part of the problem is how far away they are. These are in the Magellanic Clouds, but now that we kind of know what we're looking for, we could probably like, I don't know, like look at some clusters or things. The main thing that's like kind of difficult is you really need to know the distances very well and have like a good handle on the extinction, which is why I think we didn't have sources until now, because in the Milky Way that's really difficult to do, and outside like it was hard to get UV. But yeah, I think seeing if Lisa would be able to pick this up would be like a really cool project.
Yeah.
Hey, right here.
Hi.
Thank you very much for the great discovery. So can you come back on the X-ray luminosity predictions you have? So yeah, this one. So how well constrained is the mass loss rate from the strip star? Like, because I guess you had to assume like a certain reservoir of material, but like the orbital speeds that you see in the previous slide in the Doppler boosting is huge, right? Right, due to the low orbital period. So I would guess that the wind would have troubles to take off from the strip star itself.
Yeah, that's true. We want to better constrain the winds with UV spectroscopy, and also like an X-ray prediction would help that as well, because you're right, there are a lot of uncertainties in how X-rays would work for this, and we have assumed things about the efficiency of it. Yeah, which hopefully getting an observation like this would kind of help with those constraints, because you're right, like there are some parameters there that are really uncertain in this calculation.
Okay, thank you.
Okay, we're gonna have to wrap up. I can see hands, so please go to Bethany for the coffee break. She'll be happy to take your questions and discussion. Varsha, please enter the stage. Let's thank Bethany again.